Welcome back to The Explainer. I'm so glad you're joining us today because we're jumping straight into the hidden science behind something that is quietly but relentlessly tearing our modern world apart. We're talking about a phenomenon we see every single day, but there is a fascinating, almost rebellious science behind exactly how it works. Today, we are uncovering the true science of corrosion. Get this, 30 to 40%. That is a staggering number. I really want you to absorb the gravity of that for a second. We are talking about 30 to 40% of all the iron and steel produced globally every single year going toward just one thing, replacing rusted metal. Think about the massive blast furnaces, the extensive mining operations, the incredibly complex global shipping logistics involved in metal production. Nearly half of all that colossal human effort is spent just running in place, fighting a relentless invisible enemy. And you've seen this billion-dollar decay in action. On the bottoms of old cars, creeping up abandoned buildings, silently eating away at pipes. It's not just an ugly aesthetic issue, it's a structural failure waiting to happen. The financial and structural damage caused by corrosion across our appliances, cars, and critical infrastructure is mind-blowing. In fact, the total annual costs of massive natural disasters like floods, hurricanes, fires, earthquakes combined are actually less than the cost we incur due to corrosion. It's a massive, slow-moving disaster that literally never sleeps.
So, here's our roadmap for the explainer today. We'll start with the billion-dollar decay, move into the reversal of metallurgy, then cover dry chemical corrosion, wet electrochemical corrosion, and finally, the two paths to destruction. Let's get right into it.
Starting off with Section 1, the billion-dollar decay and its real-world impact. Let's pin down the exact science here to ground us. Corrosion is technically defined as the destruction of metals or alloys by their surrounding environment through chemical or electrochemical changes. Now, the key takeaway here? This isn't just random physical wear and tear. No, it is a systematic chemical deterioration. It's literally nature taking its toll through calculated chemical reactions based entirely on where that metal is forced to live. Which brings us to Section 2, the reversal of metallurgy, or what I like to call a thermodynamic rebellion. Think about the sheer human effort of metallurgy for a second. It perfectly contrasts with the natural process of corrosion. Metallurgy is a reduction process. Metals naturally exist in the earth as stable ores, usually combined with oxygen or sulfur. We pump massive amounts of energy into those ores to extract pure, isolated metals. We force them into this excited, unnatural state. But corrosion, that's an oxidation process. It's simply the metal's natural thermodynamic desire to release all that pent-up energy and revert right back to its stable combined ore state. Corrosion is literally metallurgy in reverse. The metal just wants to go home to the earth. Now let's look at how it actually happens in Section 3, dry chemical corrosion, the direct attack. So, dry corrosion, also known as chemical corrosion, is pretty straightforward. It happens without a drop of liquid or moisture present. It's a direct chemical attack by the environment on the metal surface. Usually this involves atmospheric gases, like oxygen, reacting directly with the metal to form an oxide layer. And here's the kicker. If that oxide layer is porous, like what we see with alkali metals, atmospheric oxygen can just keep penetrating through those pores. It causes continuous decay until the entire piece of metal literally crumbles into oxide dust. But what if moisture is involved? That takes us to Section 4, wet electrochemical corrosion, or the hidden circuit. This is where things get really wild. Wet corrosion actually transforms metals into tiny, self-destructing batteries. When a metal is exposed to a conducting liquid, an aqueous environment, this kicks off. And hey, it doesn't need to be a bucket of water. Just a microscopic film of atmospheric moisture mixed with some dissolved salts or pollutants is enough. That moisture acts as an electrolyte and sets up a microscopic galvanic cell right on the surface of the metal, generating distinct anodic and cathodic areas. So yeah, the absolute second a drop of impure water hits your car door, an invisible battery forms on the surface, ready to eat that metal alive. Let's break down this invisible circuit into 3 steps, because it really does operate like a closed loop. Step 1, anodic dissolution. The anodic area is where the metal actually dissolves, undergoes oxidation, and releases free electrons into the metal structure. Step 2, those freed electrons flow right through the conductive metal itself over to the cathodic area. And step 3, the cathodic reaction consumes those electrons. The absolutely crucial thing to understand here is that the physical destruction, the actual loss of material, happens at the anode, but it is entirely driven by the cathode demanding and consuming those electrons. Break this circuit and you stop the corrosion. This brings us to Section 5, the two paths to destruction, hydrogen evolution versus oxygen absorption. So this wet electrochemical process can actually take two very distinct paths depending on the liquid environment. We've got the hydrogen evolution type of corrosion and the oxygen absorption type. Now, the anodic reaction, the actual dissolving of the metal, is exactly the same for both. But the cathodic reaction changes entirely based on what's in the liquid. Let's zoom in on each of these. First up, in acidic environments, we get hydrogen evolution. Here, you typically have very large anode areas and small cathode areas. At the large anode, the iron dissolves into ferrous ions, releasing electrons. Those electrons travel through the metal over to the small cathode, where they're quickly gobbled up by the abundant hydrogen ions present in the acid. The result of that consumption? A violent release of hydrogen gas. Honestly, if you had a microscope, you'd actually see tiny bubbles of hydrogen forming and escaping. The metal is basically fizzing its electrons away. Conversely, let's look at oxygen absorption. This happens in neutral or basic environments, like, say, a simple drop of rainwater sitting on exposed iron. The dynamic completely flips here. Tiny cracks in the metal's protective oxide film act as incredibly small, highly concentrated anodes. Meanwhile, the rest of the vast surface area acts as one giant cathode. The iron dissolves at the tiny crack, sending electrons out to the large surface, where they react with water and dissolved atmospheric oxygen to create hydroxide ions. Because the anode is so incredibly tiny compared to the massive cathode demanding electrons, the corrosion is super concentrated. All the destruction drills a deep pit into that one tiny crack. That is exactly why a tiny little scratch on a painted surface can cause massive structural damage over time. Which leads to this fascinating quirk of the whole process. As this quote notes, though corrosion occurs at the anode, the rust formed near the cathode because of diffusion. Think about what's happening on a micro level here. The metallic iron ions are released at the anode, right? But the non-metallic hydroxide ions are generated at the cathode. These ions then diffuse. They basically swim through the water, toward each other. When they finally crash into each other in the middle, they react to form ferrous hydroxide, which eventually oxidizes into what we know as rust. So the visible, flaky rust you see isn't actually sitting directly on the exact spot where the metal dissolved, it precipitates exactly where the ions collided. And that leaves us with a pretty profound thought to wrap up today's explainer. If metals possess this natural thermodynamic desire to return to the Earth, and the very air and water around us are perfectly engineered to set up microscopic batteries to help them do exactly that, can we ever truly stop corrosion? Or are we just using brilliant engineering to delay the inevitable? It definitely frames humanity's endless, expensive battle to preserve our metallic world in a completely new light. Thank you so much for joining me to explore the science of corrosion today. And as always, keep questioning the world around you.